Hello, my name is Todd Montgomery. Some of you know me. So I won't go into who I am, but I will talk to you about what Aeron is. So Aeron is an open source project started around 2014 and sponsored by the CME to design and build a high performance, low latency messaging transport. In other words, communication and with the intention to be used within trading organizations in the front office. So exchanges, buy-side traders, anything you can think of with that low latency requirement. Aeron Archive came along, also sponsored by the CME, and it is to record and replay streams of Aeron data. And then Aeron Cluster, which was sponsored by our friends at Adaptive, which I happen to be a part of now. And that is to build a raft cluster framework on top of Aeron Archive and Aeron as well, with the same goals of low latency, high availability, and and high throughput. So we have a lot of customers who depend on us. We're now able to actually show some of them now a little bit more publicly. Just flash the logos up a little bit. This is really neat, especially if you have an open source project that started and people didn't want to admit they use you. Now some of them start to actually acknowledge that we exist and that they use us, which is nice. But really what we wanted to talk about here is some of the challenges of moving front office systems so that they're 24/7 availability. And one of the questions you may have, and a lot of people do have, is what's so hard about 24/7? If you're talking to like consumer, websites and things like that, what's so hard about 24/7? They have to be available 24/7 anyway. It's a little bit different when you start to think about it in the instance of low latency, high throughput, very demanding systems. So there's nothing really hard about it, except when you start to look at the SLAs that are very aggressive that must be met. Not only contractually, but sometimes regulatorily, right? So you have to be available. You have components that need to be upgraded. You can't just take the system down to upgrade it. It's one of the advantages of running, when you have dedicated downtime, you can upgrade the system. You know when that's going to happen. When you don't, how do you know when to upgrade? Well, the answer is you should be able to upgrade it anytime you need to, right? But you can't do that and continue to meet your SLAs, can you? Actually, you can, if you think about it. And transactions must be processed in real time. It's a little different when you don't have transactions that have to be processed in real time. So not all systems that run 24/7 are exactly the same. So it isn't hard, but it is hard in certain situations. So the things that really matter to this are the fault tolerance model that's in use, how disaster recovery is handled and how you can sort of lean on it, as well as how you do things like upgrading in production. So first, fault tolerance. I'll take you on a little journey about how fault tolerance kind of evolves and has evolved. So let's say you have a service, you have a client connecting to that service that's running on some machine, and you want to make this fault tolerant. Your service can be restarted. I mean, it means someone going in and actually restarting it by hand. It could mean someone goes and pushes the power button, because they got turned off, right? There are all kinds of things. The idea being, the first thing you may do to make this highly available is to put it on the cloud. Now, how does this make it highly available? Well, now when you have cloud infrastructure, you do have the ability to do all kinds of different things, like move it, right? It's a little different than moving it when it's on-prem. This is a form of fault tolerance. But it gets more complicated as you start to think about your service and start to add different types of fault tolerance to it. You may have multiple services, and you can go to any of them. You may have more clients, and how do they know which ones to go to? These are all solved problems. We have many different ways to solve them. But essentially, the problem that we're really trying to fix is the state problem. It's the fault tolerance of state. It's that state in the services that starts to become the thing that we want to make highly available. Most of the time, a lot of systems just kick the can down the road. What they do is they basically have a state storage somewhere else. They have a database or something else. Again, it's a way of doing fault tolerance, right? It's not my problem now, it's now a vendor's problem, because I'm going to Oracle. I'm relying on Oracle now to have this problem. But you notice that the same problem exists, it's just now moved, right? That might be good enough. So it really is this state and the fault tolerance of state that really kind of matters. And when you start to look at this, there is a continuum between partitioning that state and replicating that state. If you have the state in one place, what's the old adage? If you have it in one place, you have it in none, right? The idea being, if you lose one, it's not good enough. Regulatory-wise, you may have requirements that require that you have this state in multiple places, as well as just wanting to have it in multiple places. So we do have methods of doing this, but I'm going to talk about one specific method of visualizing this for development and for the way that Aeron Cluster works. And that's the idea of a continuous log with snapshot and replay. The thing that is actually being replicated is a log of events. Those events then are processed in order, and they then generate state. And you can at some point snapshot that state and replay that state. To sort of give an example, here's just a sequence of messages. It could be anything. It could be new order add. It could be cancel, modify, something like that. It's very easy to think of it from the trading side. And that has an associated set of state along with it that gets incrementally kind of continues on, right? It kind of gets added to as it goes along. If you were to look at any of these events, you could take a snapshot of that state at that time. That snapshot is just a roll-up of those, the effects of all the state changes. You could then kind of look at it as if I were to take that snapshot, be able to rehydrate it, and then replay the log 5 and 6 after it. Those two sides should actually be the same, right? I should have the exact same state. You can do that. There are many systems that do this basic idea. What this allows you then is a way to think about this instead of it being your snapshot of state within a database. It's just a log with snapshots and replay. In fact, most databases work this way. They have, they have a log. They do this, essentially this, with some additional things attached to it as well. But if you take this step further, so we've really just talked about how the application might look at a stream of these events and actually state change and looking at holding that state. But there's a reason why we're talking about this. We want to actually have multiple clusters of these services with local log archives, okay? So the log is replicated across them, and those services are running and they're consuming that same log. Now, each of those should have the exact same state. In fact, they should and they do. That's deterministic execution. That log will always generate the same state. When you have that deterministic execution, now all those replicas should be in the same state. This idea of replicated state machines has been around for quite some time. It is a simplification that allows you to build systems that are very highly available. So there's a couple things here. Each replicated service needs to be reading from the same event log, obviously, and they have to have the same input ordering. If the input ordering varies between them, that's not going to work, right? You have to have the same input ordering, thus the same log. And you're locally replicating the log. Okay, so there is no central place where the log is stored. The log is replicated at all the different nodes of the cluster. Snapshots are really checkpoints. They're events in the log, and they roll up previous log events or the state changes for those events. So one question that you kind of come up to first is, okay, I'm reading from this log, but there may be different spots that each service is reading from this log. How do I know when I can process a message? What happens if only one processes a message and then it's the only one to have it? Well, we don't want that. So there's a couple different types of consensus algorithms. Paxos was one of the first, but they even go back further than that into the late 80s, early 90s. Work was even being done in the 70s on they didn't call it consensus at the time, but they had the same building blocks. RAF consensus is an idea that is very simple to distill. It basically means that the event must be recorded at a majority of replicas before being consumed by any replica. This is the consensus part. So you can't just get a message and process it immediately. You have to wait until that message is locally replicated to at least, in a node of 3, one other. So you have it and another has it. So that's the basic idea of something like Aeron Cluster. It's also the other Raft implementations that are sort of taking this same technique. They're looking at that log. They have the concept of snapshots, although snapshots are an optimization. And it is the idea that you use this so that each of these are in, without intentionally making them in lockstep, they are in lockstep because they're actually reading from the same replicated log. But it has some things that make it nice for 24/7, and they may have some things that make it bad for 24/7. The first thing we'll talk about is disaster recovery. So when you're talking about recovering from a disaster, and when I'm using this term really kind of pretty loosely, the idea of a disaster recovery is not that you lost like a whole data center. It's like maybe you lost, one member of a 3-node cluster. Let's even consider that to be a mini disaster. The metric that we really are concerned with in most of, when you have tight SLAs is going to be recovery time objective. In other words, how long does it take before you can get back into operation and continue operating? And you want that to be low. And you want that to be low in all cases of disaster recovery. That would be the ideal, right? Lose a whole data center, lose all 3 members of the cluster. You still like to be able to, in disaster recovery, bring that up within seconds, ideally, right? So how does this look when you start taking into account the idea of disaster recovery? Well, the first thing is remember that snapshots, could be lazily disseminated. The idea being that when a snapshot is taken, it's really an optimization. You could still just use the log, right? And it's because it's an event log, you could lazily disseminate these to the other members or to DR, and you could stream the log as it reaches consensus to DR. So, as you take snapshots, a new snapshot comes along, it could be lazily disseminated. If you had a failure before that, you could use the previous snapshot until, you get the snapshot disseminated. But this brings up an interesting point. You could run this in a cold scenario where this data is being stored in disaster recovery is simply just cold. There's no, it's not running hot. It's just storing the snapshots. It's just storing the log. Or you could even be really cold and put it in like S3 or something, right? So it could be, even in that kind of scenario, it's very cold. Or it could be kind of warm. In other words, you have service logic that's running on that log and it's sitting there ready to take over in case it needs to. So let's break this down. For a cold replicated state machine recovery, it's a little different than warm. The first thing is with a cold recovery, you first have to load a snapshot, then you have to replay the log. And if we break that down sort of in the view of we have loading the snapshot, we have a couple messages here in the state that gets generated. You break it down into 2 steps. The time to load the snapshot, and then the time to replay the log. So why does this matter? Well, let's say that you're snapshotting once a day, every 24 hours. What's the worst scenario? You've got a snapshot that is 23 hours and 59 minutes and 59 seconds, 0.99 seconds old, right? How long does it take to replay that when you're sending millions of messages a second? A long time. It's not I/O bound, it's compute bound because it's replaying and doing all the different things it needs to get this state. So it's realistic to think that you could have a situation where you're replaying that much data and have to reconstruct it, and that's time where you're not participating in, and actually being a node in the cluster. Can't until you catch up. So that means that the loading a snapshot is small, typically-ish, and it's large, the time to actually replay the log. It can be large. So how do you fix this? Well, a couple different options. The first is you can actually snapshot more often. Suppose you snapshot every hour and you know that you can run through an hour's worth of data in, say, a minute. And that might be good enough, right? Your SLA may be that, in certain types of situations like this, you're able to come back within a minute, replay, and be caught up to speed. That's great. And that means really what you're doing is you're just making it smaller log to replay. But you then have more snapshots. Well, so what happens about the impact of taking a snapshot? You know, anything we do on a machine perturbs it. In fact, if you work in low latency, you're very aware of this. Trying to quiet a machine is a very intense process of trying to find out what is going on the machine that is changing and making something else slow. So taking a snapshot is going to perturb the machine in some way. In fact, it does more than that. In Raft, taking a snapshot is an event in a log. You then have to have all the members take that snapshot at the same time in the log. Guess what? Nothing else is being done while they're taking that snapshot, right? So that's a disruption. But if you were to instead think of it as having something else that asynchronously takes that snapshot and disseminates those snapshots back into the cluster nodes, that is one way to think about, reducing the impact of snapshots. That doesn't just solve that, snapshotting more often. It helps, but you still have the problem of if you're going to load, a snapshot and then load a log, and you're not willing to go for a couple minutes while you're doing that, how do you go faster? You have to have something which is at least warm. And then the idea is having a service replica, running your logic in DR, ready to be hot in a moment's notice. You don't have to be an active node in the cluster. You're the one, the standby or that other node is just pulling across the snapshot, it's pulling across the log. It's processing it just like a normal node was. It's just not an active member of the cluster. If an active member of the cluster goes down and you want to replace it with that, you just have to tell it, join cluster. And that idea of being able to just swap in, a crash node with a node that's warm and letting it go hot, what kind of delay is that? We're seeing it's only about a second or two. Most of that can even be reduced as well. So you're thinking of something like NDR. It is possible to run NDR, something where you have a full copy of a cluster running. You lose the data center. You can start up NDR in seconds. That's kind of powerful, right? Because that means that it's like, oh, we lost the data center. We had another heat event, like we had in the summer, right, in AWS. And then be able to be right back in it within seconds. That's pretty nice, right? That's the kind of idea that we kind of think about, what has to happen for a lot of systems. 24/7 upgrades. So that's kind of there's a couple different things there that we talked about in terms of what it actually means to look at how you can, get basically things from a disaster and recovery and recovery time. But let's look at another cause of, when you're running 24/7 of how you're going to do upgrades. So you're going to do upgrades probably by stopping everything, right? You're going to do a big bang. You're going to actually do a forklift upgrade. Actually know people who do this. They actually take a forklift with a whole rack, pull it out, and put another, rack in its place. I'm not joking. There are businesses that do this. But that's not going to work, right? There is a significant amount of downtime that's going to happen no matter how you do that. So how do you do this? No, let's say that we run two systems. One hot, okay? One that is, let's say it's warm, and we upgrade that one, and then we switch over. How long does that switch over take? A couple seconds? Is that too long? It might be. If you're doing a couple second outage, 4 or 5 times a day, people don't want to upgrade, right? So that's a barrier. You want to make it so that upgrades can be done quickly. So the first thing is you have to really kind of absorb the fact that components will be on varying versions. No matter how you're doing an upgrade, you can't just do it all at once if you're going to be live while you do it. And that means including the infrastructure. Things like Aeron Archive, Aeron Cluster, these have to work in situations where they're running multiple versions in production. Now, that's something we take on, right? But we don't think that it's any different. If we say that, you should do it, we have to also do it too, right? And we do. And I mean all components that you have. The cluster is only one piece of usually larger systems, so all of them might be on different versions. The best thing here is protocol design and lessons that have come from that. So about how to make protocols so that you can have multiple versions running and how you do things like, backwards compatibility, obviously, but forwards compatibility. So what does forward compatibility mean? It means that you put forethought into how might things change and how can I catch that there is a new version that is safe to not interoperate with, and things that are safe to interoperate with. By putting several little bits in messages, that's one way of making them forward compatible, because you think up front, how do I handle this when I don't know what to do? You can give a little bit of additional information. There's specifically things like IPv4, TCP options and other things have this in mind because they know they're going to be operating in situations where there's never going to be the same version. So they have like ignore bits in options where you can ignore this option and keep processing. But if you don't understand it and it doesn't have the ignore bit set, you have to throw the whole message away. That type of simple thing can then be leveraged when you're actually doing things like that. Other thing is version everything. And I mean everything. Messages, data in REST, data in database, everything should have versions attached to it. Your future self will appreciate this to know sort of a lot more things later on. The concept of semantic versioning is a powerful one. It is a versioning scheme that has very strict rules about what is compatible and what's not and how you version based on it. When you have this, you can leverage that idea to figure out if that's a message or a piece of data that you know how to handle and ones that you may not know how to handle. So upgrading during production, rolling upgrades. What we have seen is this sort of scenario. You have a service that's running various versions. In this case, they're running the same version because we're going to upgrade all of them. And so you basically do the simple thing. You're leveraging Raft. You're leveraging the idea of your high availability. You're taking one down and upgrading it. You're continuing to operate because you have two. The obvious problem here, I will address in a minute. But you do this. Now that is upgraded. Now you start upgrading the second. At that point, notice you have two versions in production. You have two different versions that are live and active in production. You have to have that. So the idea that you're going to have this and just accepting it is fundamental to being able to do that. And we do the last one. And then we're done, and everybody's upgraded and happy. A couple things to realize about this. The obvious problem here is that when you take one down, you're operating at risk. And the idea of operating at risk is you have one node failure and it will stop and stall processing because you cannot reach consensus. So during that process, when you're doing the upgrade of one, you better hope that they don't fail. How do you address that? You use a larger cluster. So 5 nodes, you can upgrade one at a time and not be running at risk. Now you can only, withstand one failure, but that's fine. If you're thinking about it, if that is your bar, then doing it. Does that mean that you should grow the cluster to 5 and from 3 and then go back to back to 3 when you're done? Actually, no. If you're upgrading all the time, why would you want to do that? Why don't you just run 5, right? What some of our customers do that use Aeron. They run 5, and this is how they do rolling upgrades. Just simply take one down, they're not running at risk, they then upgrade that one and just continue to do that. But here's an interesting part about math. The majority of 7 is 4, right? So you can actually upgrade, can actually upgrade 2 at a time when you run a 7-node cluster. It's actually faster to do it that way than to run 5, right? With 5, you have to do one right after the other. That's 5 times. So the time commitment is, 5 times whatever it is for 1. When you do it with 7, it's 4. It's an interesting thing to consider. So there's lots of other implications of when you start to version everything. Your log now has all kinds of version history in it. That's kind of interesting, isn't it? So you have all these versions. You can see when they change. You know exactly when they changed. The message event that when they changed. That's an interesting thing to think about. So this has some interesting side effects when you start to put versions all over the place and start thinking about running with the different versions in production. Here's some hard lessons, though, that we've seen. Retaining old broken behavior forever. You almost have to. So here's an example. Let's say you're in Exchange. Let's say that you have some broken logic. Let's say that you executed that broken logic at some point. Now, it probably had no effect on the customer, but it has an effect on you for a regulatory reason. If someone, let's say you're operating in the EU, 7 years that you have to be able to retain that data. You also have to go back 7 years to look and see the logic that you executed on that data. It's an interesting thing to think about, right? You may have to not hold on to that broken data or that broken logic in your actual app and running, but you may have to be able to go back to it and say, here's how this happened. So that's an interesting thought, is how you have that, because that log stays around for a long time. The clustered services are often the easy part. Kind of, if you look at this, a lot of design goes into how you're going to actually handle different versions, when you're going to upgrade, how you're going to upgrade, doing rolling upgrades like this, and being able to continue to work while you're doing that. And then how you coordinate this as a system with the external things like gateways attached to it, stuff that's downstream that is processing data, even databases that are attached in other places. So it's usually the cluster itself and the cluster nodes, those are the easy things to upgrade. The hard things are the things like everything else that's attached. And that's where when you started to think about the fact that you may have multiple versions that are running in production and how they interoperate, you actually make the whole system cleaner, because you can now use some of those techniques that you probably learned downstream as well. Feature flags are not version. They're not versions. Seen this many times where people look at feature flags and they put them in a version and then they want to upgrade the version, but that means that they just want to add a feature flag, which means they have to update the version. Why not have the feature flags totally separate from versioning? That's something that's usually a lot better. Decouple feature flags and versioning. And the last thing is leverage determinism. You have determinism. Realize that now, reading that log, there's a lot of stuff that you can do with that logic. So leverage that for testing. Leverage it for the fact that you can run that same test over and over and over, and it will give you the exact same state. That's a powerful thing. Just don't put things that are non-deterministic in there, because then you'll have to be chasing them for a long time. Anyway, these are just some of the things that we've seen as we've seen a lot of users of Aeron move from going from a lot of times where they had some dedicated downtime, maybe once a week, not a whole lot, but I'm talking about something where they had a window to no window at all, where they have to operate 24/7 and maintain the pretty aggressive SLAs that they normally have. Thank you. Any questions? Yeah, the backup, and this works also with standby as well. So the backup or the standby, the entity that is in disaster recovery or somewhere else, it's the one who's going to the archive of the node, and it's going to a follower. It had been going to a leader. We've changed that recently, so it goes to the followers instead. And it load balances between the followers. And it pulls across those things as they are, being, in the case of the log, as it's being generated, in the case of the snapshots, as they are occurring. Mm-hmm. So we're in the process of doing asynchronous snapshot support as well. And in fact, it'll be one of the jobs of the standby. is that can be done like that. What we've seen is that people have tried various things to do asynchronous snapshots. The most common thing, I think, is not thinking of it asynchronously enough. There's a natural tendency that when you want to take a snapshot, you want to get it back into the cluster as quickly as possible and get disseminated. And it's actually better to let that be lazy. So one of the things we added a while ago was when doing various things is to actually put I/O length on the work that's being done in the archive. And the intention there is to do it so that we go slower, intentionally, to be less perturbation on the system, in that case. So it's sometimes patience pays off. So in that case, it's take the snapshot asynchronously, and if it takes 10 minutes to disseminate it, as long as and you're doing it slowly, you're being less perturbing to the system. It's better to do that than to do it too aggressive. Now, if you want to make sure that you get that snapshot, disseminated because of other reasons, you may have other reasons that you want to make sure that you may have other work you want to do with that snapshot. You might want to, you have full control over how you want to do that. But yeah, that's the common thing of just not being patient enough, thinking that it has to be there now. I have no idea. Kafka traditionally does things in a kind of a little bit different manner and thinks about things a little bit differently. It's not so much, unless they've added it recently, there's not really a whole raft implementation in Kafka. You can build systems that kind of look like this with Kafka. You can, if you wanted to, write something yourself that, does consensus, has its own voting, and underneath the covers uses Kafka. It's going to be slow. So when I say slow, what is that, right? So the fastest we have run, a cluster is 1.8 million messages a second coming in, and at the same time, being able to round trip a message from a gateway through the cluster and a response coming back out, and having the P99 of that response, that whole round trip being less than 20 microseconds. So on-prem, SolarFlare cards, EFVI, but you can get these systems to run very fast. I think to run something like 1.8 million messages a second with Kafka, and that's 3 machines, I don't think you run a Kafka cluster 1.8 million messages a second, with 3 machines. I don't think so. This was 32 byte messages. Mm-hmm. We're just looking at, and that was maxing out 2 25 gig NICs, one for consensus and one for the log. Lots of detail on that. But essentially what that is how far can you push cluster? And you can push it very, very far. But that's as fast as we've been able to push it. I'm not sure. I think from the normal way that I believe that kind of architecture works, what you're doing is you're extending the Kafka, the Kafka nodes, the Kafka services into DR in some way. It could look somewhat how we do warm standby or cold backup, that kind of thing where you're extending it into. But I don't know the details of what they do. Traditionally, if you look at most brokered architectures, they do that by bridging, into DR. And that means they get very slow because they're round tripping everything through DR. We're fundamentally not. We're asynchronously streaming into DR. All right, thank you.